All right, welcome back to Math for Healthcare video lecture series. Today we're going to be looking at probability applications, accounting principles. This is the third time I'm recording this one, so hopefully it works out. I've had sound issues gaining on me. So, we've been doing counting, and we're going to continue doing a little bit of counting, but here we're going to start looking at it in terms of probability. I want to remind us that the reason we look at probability is it's a way for us to measure against random events, right? You know, we always want to say, well, and we as humans, we get fooled by randomness. It's very easy for us to put meaning into things that are just random events, and that's the power of probability, is a kind of a way to measure, well, what's the chance of this happening randomly? Okay. So, going back to our definition of probability, in a finite uniform sample space, that just means in our sample space, it's broken up to equally likely events, and they're finite. We just look at the size of the set of the event over the size of the set S, or the sample space. Alright, so what's the probability of two heads when tossing 5 coins? Alright, well, here, what's going on? First of all, hopefully by now we're pretty good at finding the size of the sample space. Alright, sorry guys. Size of the sample space here is going to be, remember, basically we're thinking this is like a Venn diagram. I'm sorry, not a Venn diagram. We have 5 slots. They could each could be either heads or tails. That's why I write the 2, right? So what do? We do 2 to the 5th. Multiply all, use our multiplication principle. Remember, when you're doing those multiplication principles, what you want to find or realize is that really there's a tree diagram going on underneath it. All right, so that's the size of our sample space. We're good there, 2 to the 5th. How about getting 2 heads? Let's think about this here. So now we still have these 5 slots up here, right? Let's think about what makes 2 heads. Well, let's number these slots 1 through 5. 4, 5, right? And you can imagine what is 2 heads? It means 2 of those 5 numbers, 2 of those slots are heads, and the rest are tails. All right, so we could look at this problem as saying, how many ways are there to pick 2 things from 5? In other words, I got 5 things in a bin, and hopefully this all makes us think, oh, okay, we got 5 things in a bin, and we got to choose out 2. How many ways are there to do that? That's going to be 5 choose 2, which is 10. Okay. Now, all right. Hopefully that makes sense to us. Think about it. If I reached into a grab bag with 5 pieces of paper that have these numbers 1 through 5 written on them, if I pulled out, say, 2 and 4, right? Well, that would be one of these up here, where I have a heads and 2, heads and 4, and then the rest are automatically tails. All right. So, and then what we get is that the probability of our event E is 10 over 2 to the 5th, which we'll use Desmos to use our calculator. We got 10 divided by 2 to the 5th. All right, and that's approximately 0.31. And just as a reminder, if you wanted to put in the choose function there, it's n capital C lowercase r, then parentheses 5 comma 2. That's our 5 choose 2, and you see there that's 10. Okay, good. So 30% chance that we get. So if we toss 5 coins, we get 2 heads. pretty reasonable to us. 30% chance that happens randomly. We're not going to think the die is loaded, right? By the way, if we got 0 heads, what's that going to be? There's only one way to get 0 heads. We still have the same sample space, so that's 1 divided by 2 to the 5th. Oh, wrong one. 1 divided by 2 to the 5th. And that's only a 3% chance, so we may be a little skeptical. All right? Nothing definite, just slightly skeptical. All right, let's see here. We got 1959, a world record was set for the longest run on a fair roulette wheel at the Sail San Juan Hotel in Puerto Rico. The number 10 appeared 6 times in a row. What is the probability of the occurrence of this event? We're going to assume there's 38 equally likely outcomes consisting of the numbers 1 through 36, 0, and 00. So, let's see here. How can we think about this? Well, first, what it's asking us is, what's the probability that a 10 appears 6 times in a row, given that you're spinning it 6 times? Okay, right? Because it's going to change it if you thought about 6 times in a row if you spun the wheel 500 times. Right? So here it's really asking, if 10 appeared 6 times in a row, and you may also ask yourself, well, how about any number 6 times in a row? So let's first start with 10. Okay, so first, we always, the size of the sample space. How many different outcomes are there? Well, think about it. We're moving it 6 times, right? How many possibilities for each turn? 38. And so the sample space is 38 to the 6th. Now, let's say the event E is getting a 10 6 times in a row when you're spinning it 6 times. There's only one way to do that. And so our probability of E is 1 over 38 to the 6th. We'll calculate that in a second. Now, let's say event F is getting any number 6 times in a row when spinning it 6 times. There we got, let's see, there's 38 possibilities, and the probability of F comes out to be 38 over 38 to the 6th. This is F here. And that gives me 1 over 38 to the 5th. We'll check those two numbers just so we have an idea what they're telling us. Let's see. 1 divided by 38 to the 5th. Okay, so that's somewhere about 1.3 times 10 to the negative 8th. Quite small. Quite small. All right, and then let's see what happens when we look at 1 over 38 to the 5th. Oh, I did one, sorry. Probability of F is going to be 1 times 3 times 10 to the negative 8th, whereas the other one should be that times divided by 38, or 1 over 38 to the 6th. Oh, that's 10 to the negative 10. It's 3.3. You can read it on my screen. That's 3.3 times 10 to the negative 10. Slightly smaller. Well, quite a bit. It's 2 orders of magnitude smaller, but they're both of them are absolute quite small. Okay. Now this is where we start looking into measuring randomness. So let's start by first asking, say a group of 5 people select a random. What is the probability that at least 2 of them have a birthday? So first of all, let's see. What's our sample space? Let's worry about that first. What do we got? We got 5 people. And, okay. But we are going to assume all the birthdays are equally likely of the year. We're not going to count leap years. So that we have 365 days and they're all equally likely. Probably not true, but maybe approximately true. So what do we have? For the size of our sample space, we have 1, 2, 3, 4, 5, 365 for each person, right? That's all the possible birthdays that we get. Right. This is 365 to the 5th. Now, as far as counting the numerator, what we really want to use, it becomes difficult because there's lots of ways two people could share a birthday. Two could share it, three could share one, two could share one, three could share another. So what we're going to do is find the complement of what we're asking for, and that is how many ways can 5 people cannot share a birthday? Okay, so let's think about that. So cannot share a birthday. Well, we still got the 5 slots, and we gotta. There's 365 for the first one. Oh, what about for the second? Oh, 364 now because the second person can't be the first person's birthday, and the third person can't have either of those birthdays. 62, 361. We multiply those all together, which is the permutations of 365 things taken 5 at a time. Alright, so in the end, what are we looking at? Our probability of 2 people sharing a birthday is 1 minus permutations of 365 things taken 5 at a time divided by 365 to the 5th. And we'll check that out. It's going to be 1 minus NPR now, because these are permutations. 365 things taken 5 at a time, and divide by 365 to the 5th, which is our size of our sample space. So here, with only 5 people, the probability is pretty low, about 0.027. Right, so somewhere about a 3% chance. But that's a small number of people. Let's see what happens when we calculate it. I'll give you a list, but let's look what happens as n gets bigger. This is a formula up here if you wanted to look at for solving it in general, but I think you just put it together yourself if you're asked about it. How here we get the probability, what we just found, right? When n is 5, the probability is about 3%. 10, it's about 10%. 15, you're at 25%. So right there, even I'd say, why is this interesting? It's like because if you were in a room, maybe a more extreme point. Let's go up to 22 people in a room, and you find someone shares a birthday. Humans may tend to want to put meaning to that, but there's really not. There's a high percentage chance that that happens through randomness. And there's lots of events in life, in the medical field, that's a lot of it is looking at how drugs are used, what they're used for, how well they work. All that stuff is we got to measure against randomness, okay? And here, this is saying, like I said, there's a 50% chance that at least 2 people share a birthday. That's a high percentage of it happening. It's hard to attach meaning to something that has that high a percentage of happening randomly. Just to finish up, we go up there by 40, we're at 90%. 50, we're at 97%. Still would seem pretty, a room like this, room with 50 people and you share a birthday, you're going to maybe put some meaning there. And by 150, we get basically 1. Okay. So that's a little bit more of there's using we had to use the complement rule, right? And use permutations to count the idea of probability, but we also are learning how do we interpret this? Why are we learning it? Okay, so now let's say unbiased coin tossed 10 times. What's the probability the coin will land heads on the first and last toss? Okay, first of all, our sample space is going to be on the first and last toss. Is tossing the coin 10 times, 2 to the 10th. Right? Hopefully that's becoming noticeable now. Now, how about lands heads on the first and last toss. How many ways are there to do that? Well, if we fix the last two, the first and the last one, as heads, the 8 in between can be either heads or tails, and that's going to be 2 to the 8th. So we get our probability is 1 over 2 squared, which is 1/4, right? 2 to the 8th or 2 to the 10th is 1 over 2 squared. 1 to the 4th. Sorry, 1/4. Now, what is the probability the coin will land on heads? Exactly twice. So we saw this problem with 5 times. So now similarly, we still have the same sample space. This is 2 to the 10th, as the previous example. But in here, anyone's exactly twice, so you should be able to do this on your own after that first slide. And this turns out to be, like we saw before, 5, choose 2. And now here we get 10 over 2 to the 10th for our probability. And that comes out to be, let's just see what that is. 10 divided by 2 to the 10th. Alright. Now that's only 0.0097. About. Pretty small. So here, toss the coin 10 times, you get exactly 2 heads. Well, it may be slightly, you may be suspect of that coin. You can't determine anything, but you may be suspect of it. All right. Now, I want to go back to this last one. Notice I have this word binomial. This idea of coins tossing, this is a binomial probability, all right? The main thing for us is we're just think of it like anything that's like tossing a coin. It doesn't have to be equally likely. It could be things like tossing dice. We'll go over more precise definitions, but you think about this as each time you toss a coin, it's independent of the other time you toss the coin, right? That's the binomial. Now over here, we got a barrel of apples. I kind of could call this good, bad problems. 8 apples, 3 of which are rotten. Find the probability that you get 2 rotten apples if you randomly select 2 apples from the barrel. All right, so here, what do I mean by good, bad? Is I picture, when I'm finding the sample space, I picture one bin with all the apples mixed together. What do I got? 3 rotten, yep. And so they're all mixed together. I can't really tell the difference. I'm just reaching my hand in there, so we get 8, choose 3. All right, now, when we look at our event E, we think of it as 2 bins. One with the bad ones, or the rotten ones, and one with the good ones. And we're going to reach in each of those. What are we going to do? We got 3, choose 2 ways to choose the 2 bad ones, because we're forcing 2 bad ones there. And then we have, how many left? 5, choose 0 of the good ones. And this gives me 3. All right? So the probability of this event E is equal to 3 over 8, choose 3. We'll calculate that. Oh, what did I do? I made a mistake. There was 3 rotten apples. The sample that we're taking out is only 2. I apologize. This is 8, choose 2. My denominator is 8, choose 2. And in fact, we should be able to I'm going to get the number first and then speak about it. All right, looks like about 10% chance or 11% chance. That's, so the probability, sorry, there it is. 8, choose 2, and that's 1 about. Right? Now, we should be able to check how I got that wrong, as I should have been checking as always when we do these problems, when we count all of them over here, and then we have them separated. Notice that 2 plus 0 is going to always equal this 2, or this number plus this number equals this number. And then this 3 plus this 5 is always going to equal our 8. checking yourself there. All right, now I'll go back to this last one quick again, like I did the last one. We call this hypergeometric. You could call it good, bad problems. Here, it's very similar to coins, except they're not independent, right? If you picked one apple out, then the probability changes the next time you go. That's different than like when you flip one coin, then you flip the next coin. So it's the independence that really changes them. You could think of them as the good, bad problems. Here we got a group of 100 nurses. 5 are to be selected to present a list of grievances to management. 75 nurses are female and 25 are male. What is the probability the group of 5 has at most 2 females? All right. Well, first, let's find our sample space. I don't like the red so much. That's going to be what? This is now all of the one bin problems, so there's 100 total, and we're choosing 5. Now, the size of our event is, what is the probability the group has at most female students? Well, they could have 0 then, which is going to be, so female nurse, so 75 choose 0, 25 choose 5, or they could have 1, 75 choose 1 times 25 choose 4, or they could have 2, 75 choose 2, 25 choose 3. All right? Now, so the probability, take those, I'm going to enter it fairly quickly. So 75 choose 0 is 1, so I'm just going to do, first of all, I want parentheses because I'm adding and dividing. We have NCR 25 choose 5 plus 75 choose 1 is just 75 times NCR, and that's going to be 25 choose 4. And lastly, we have our 75 choose 2 times 25 choose 3. And we divide by our sample space, which is 100 choose 5. And we get about 0.098, almost 10% chance. So there, 10% is fairly large. Remember, that happens 1 in 10 times you do this. But you may be skeptical if you only get 2 female nurses. You wouldn't be as skeptical as switched, right? Though the probability would be much different if the 25 were female and 75 were male. But these are the types of things you got to. This is again measuring against randomness in order to try and get an idea if we could find some meaning there. Okay, find the probability of getting 3 heads when tossing 7 coins. That's supposed to say. Now we're back to, this is now a binomial problem again. All right. And here, our sample space is, what do we got? 7 coins, so is 2 to the 7th, right? 2 to the 7th. And our numerator is going to be, which of those 7 are going to be heads? Well, there's 7 choose 3 ways to do that. And here we get, let's see here. NCR 7 choose 3 divided by 2 to the 7th. Okay, 0.27, about a 30% chance. All right. Find the probability of rolling 3 2s when rolling 7 fair dice. This is actually another binomial problem because the dice don't have memory. It's independent. If you roll one dice and you roll the next, the probability doesn't change. All right. But here, it's a little trickier. All right. We're going to have to dive deep because here, let's see, we could find the sample space, the size of the sample space still. That's how many? There's 7 fair die. There's how many possibilities for each die? 6. Same thing. So we get 6 dashes. Each one of them has 7 dashes. Each one of them has 6 possibilities. So this is going to be 6 to the 7th. Now the numerator, that's harder to do. Why is it harder to do here? Because sure, we could count which 2 are the 3s. Okay, that's looking something like 7 choose 2. Oh, 3 2s, so 7 choose 3. It's a little confusing. 7 choose 3. Oh, but wait, they're not weighted because heads, tails with the coins, those had different probabilities. All right. Sorry, with the heads, tails, those were both 1/2. So they were all weighted the same. Here, getting, let's say we got a 2. 3 2s. 2, 3, a 2, and a 4, and a 5, and a 5, right? Okay, well, sure, that's one way to get those 3 2s, but anything, other ones that don't have, let's say we have 2 2s, 2, 3, 3, 2, 4, 5, 5. Now here, the probability of this not being a 2 is 5/6. The probability of this being a 2 is 1/6. So they're a little different. We're going to cover this in the next video and really dig into what a binomial distribution looks like. All right. Have a great day, and I will see you next time.